This conference will now be recorded.
Hello everyone. In this chapter, how to prepare carboxylic acid, that we have seen. That is all the methods for preparation of carboxylic acid we have seen, and based on that, we have discussed some problems, and some more problems we'll discuss. After finishing it, there will be physical properties for carboxylic acid, and also after that, chemical behavior of carboxylic acid. That means all the chemical reactions that are given by carboxylic acid, that will be discussed. So in this slide, one problem is left, and it is saying that C2H2. Now C2H2 means acetylene. AC triple bond. We write it here. AC triple bond CH. First, we are treating it with AgOH 1% and H2SO4. Now, when it is AgOH, it is basically containing this Ag ion, and here the condition is acidic in nature. Now, when it is this condition, we already know that under this condition, acidic condition, and mercury ion will be present. What happens? First, there is hydration reaction. So, hydration reaction means H will be inserted and also OH will be inserted. Now, this is symmetrical, so we don't have to decide which side OH will be added or not. It will be simply HC 1H. Now, there is double bond OH and H. But remember, this is enolic type of structure. Why it is enolic type of structure? Because if you focus on this part, it is CC double bond followed by OH. So that is why here, after tautomerization, the new structure that will be getting is like this. So this OH bond will be broken and CO double bond will be formed. And as a result, this CC double bond, that will be broken. So negative charge over carbon. So this H, now it will be shifted to this carbon. So finally, what we are getting, H3C, C double bond O and H. Fine. So after the first reaction, that is A, what we are getting? We are getting CH3COH. So this is the structure of A. But this is not end of the reaction, because in the second step, we are also using oxidation condition. So this type of sign, it means it is oxidation. An aldehyde, when it is under oxidation condition, that means B will be formed. And what is the structure of B? It is obviously acid. So it will be carboxylic acid basically. So what will be the correct answer? An acid. Because we have to find the structure of B, not A. A is the compound which is CH3CHO, that is acetaldehyde. But after that, it is undergoing some oxidation condition. That means now it will be oxidized to acid, carboxylic acid. So option A will be correct, not option B. Because option B, if you choose, that is actually the structure of A. But acid is structure of B. So that is why this is the correct answer. Next problem. Identify the most suitable reagent for the conversion of ethanol to acetic acid. Now, ethanol means what? Al, that means it is aldehyde, and eth means 2 carbon. So, aldehyde, 2 carbon aldehyde is CH3CHO, which is nothing but acetaldehyde, you can also say. Now, we are converting it to acetic acid. Acetic acid is 2 carbon carboxylic acid. So, from aldehyde, you are trying to prepare acetic carboxylic acid. Same number of carbon. Before reaction 2 carbon, after reaction also 2 carbon. So this is oxidation reaction, oxidation of acetaldehyde to acetic acid. And we have to find the most suitable reagent. Now as this is oxidation reaction, that is the condition must be some oxidation condition. Reducing condition you cannot use. So this option cannot be correct. This is absolutely wrong. Now rest of the reagent, if you see, all these are basically oxidizing reagent. Now among this oxidizing reagent, as we have to choose the most suitable reagent. So not just any oxidation condition randomly you can choose. You have to choose the most suitable condition. Now, when I'm saying most suitable condition, what it means? It means if the condition is very mild in nature, as mild as possible, that method will be best. Now, among these three oxidizing conditions, the most mild condition is tolerance reagent. Okay, so in tolerance reagent, basically silver plus is the oxidizing agent, and silver plus, though directly we do not use this ion, there is some silver amine complex. You can also check the slide where I have discussed tolerance reagent, which is this test, tolerance test also you can say, which is basically used to identify aldehyde group is present or not. Okay, because it can oxidize aldehyde to carboxylic acid. So Ag plus, it acts as oxidizing agent and it reduces to Ag0. That means it is accepting electron, so it is oxidizing agent. But this condition is very mild condition, not like alkaline KMnO4 and then treating it with under acidic condition, or Jones reagent where chromium reagent is used. Fine. So tolerance reagent is the most mild condition among these three. D is already you can reject this option because it is reducing agent, but you have to use some oxidizing agent, right? So D is already cancelled, and among ABC, the most mild is tolerance reagent. So this should be the most suitable reagent for conversion of ethanol to acetic acid. That means from aldehyde to carboxylic acid. So aldehydes are easily oxidized to carboxylic acid having same number of carbon atoms. You can check before reaction 2 carbon, after reaction also 2 carbon. So there is no CC bond cleavage. As the parent aldehyde when reacted even with mild oxidizing agent like tolerance reagent. So as the aldehyde, which is basically the starting material, it has very good reducing property. So when it has very good reducing property, very mild oxidizing agent also will serve the purpose. That is, the purpose is to oxidize aldehyde to carboxylic acid. And as aldehydes are very good reducing agents, so mild oxidizing agents are enough for this conversion. So option C, that will be the correct option. Tolerance reagent. Which of the following pairs doesn't give the same compound on heating with alkaline potassium permanganate? Following pairs. So in each option you have two compounds, and you can see all are benzene derivative, right? And what type of benzene derivative? Some alkyl substituents are present. If you look at the options, toluene, that means it is CH3 group attached to benzene ring. That is the structure of toluene. Then propyl benzene. Propyl group is 3 carbon chain. So 1, 2, 3. So this is propyl benzene. Then in option B, again toluene and N-butyl benzene. Now when it is N-butyl, that means 4 carbon chain will be there. 1, 2, 3, 4. Then propyl benzene again, which we have already drawn the structure. Isopropyl benzene. What is isopropyl benzene? This is isopropyl benzene. Now try to understand the difference with propyl benzene. Propyl benzene also 3 carbon chain, but this is simply a linear chain. In the terminal carbon it is attached to benzene ring, but here it is not so. The middle carbon is attached to benzene ring. That is the difference between normal propyl chain and isopropyl chain. So this is isopropyl benzene. And in option D, orthoxylene. Now orthoxylene is basically 2 CH3 group at ortho position. Now it may be, that is the common word is xylene. If it is orthoxylene, 2 methyl groups are 1 and 2 position. If it is metaxylene, 2 methyl groups 1 and 3 position. If it is paraxylene, then 2 methyl groups 1 and 4 position. And N-butyl benzene, this structure we have already drawn. Now all these molecules, they are heated with alkaline potassium permanganate. Now when I'm saying alkaline potassium permanganate, that means it is obviously the oxidizing agent. And what it does, any alkyl group that is attached to benzene ring, that will be converted to CO2H. Now when it is toluene, after treatment with KMnO4, what we will get? We will get simply benzoic acid, 1 carbon. Now there is no confusion, you can easily understand. CH3 is converted to CO2H. But remember, very interesting thing, though it is already discussed, that is how we can prepare carboxylic acid, that is any aromatic carboxylic acid. Fine. That is benzene ring directly attached to CO2H group. So there is a specific methods for this type of carboxylic acid synthesis, and that method is oxidation of side chain of benzene ring. So any alkyl chain, whatever is the nature of alkyl chain, for toluene it is single carbon, but for N propyl benzene it is 3 carbon. But though it is 3 carbon, but still you will get the same molecule, which is benzoic acid. So from propyl benzene also, that is from this molecule also, you will be getting benzoic acid, because the reason is the cleavage will be in this CC bond. Rest of the 2 carbon, that will be decomposed. Fine. So the carbon which is directly attached to benzene ring, only that will be remaining in the form of CO2H. Similarly, that means from both toluene and propyl benzene you are getting the same molecule, which is benzoic acid. So that is the question. It is asking which of the following pairs does not give same compound. So option A, both the compounds giving you same compound, which is benzoic acid. Now option B also, toluene, you will be getting benzoic acid, N-butyl benzene. Again, this carbon which is directly attached to benzene ring, only that will be remaining. Rest of the part will be lost. So again you are getting benzoic acid. So option B also you are getting same molecule. Then what about the third option? In the third option also, propyl benzene you will be getting benzoic acid. Isopropyl benzene, here also these 2 carbon will be lost. So you will be remaining with this fragment only, and the carbon is benzoic acid. But the last one, this is different. Now when it is orthoxylene, you are treating it with KMnO4. Basically you will get 2 CO2H group at 1 and 2 position. So this is not benzoic acid, right? Because you have 2 CO2H group. So this is the oxidation product from orthoxylene when you are treating it with alkaline potassium permanganate. But when it is N-butyl benzene, basically you are getting benzoic acid. So you are not getting same molecule as product. So that is why this should be the correct option, because the question is asking which of the following pairs does not give the same compound. Fine. So option D, orthoxylene N-butyl benzene, this will be the correct option. So after finishing the problems and related to synthetic methods for preparation of carboxylic acid, now we are switching to physical properties of carboxylic acid. Now when it is physical properties, the first physical property we are going to discuss is physical state. That means whether they will be liquid, solid, or in vapor state. If we consider aliphatic carboxylic acid, up to 9 carbon atoms, not after that, then they are colorless liquid if it is at room temperature, that is around 25 degrees centigrade, and there is unpleasant odor also. So remember, it is only applicable for aliphatic carboxylic acid and up to 9 carbon atoms, not more than that, because if it is more than that, now it will be now having more molar mass, and when it is more molar mass, the physical state will be changing from vapor to from it is I mean to say it will gradually change from vapor to liquid to solid. Now as for aliphatic carboxylic acid, it is already liquid up to 9 carbon atom. That means if you are going beyond that, now they will be solid. So that is why, to come to the second point, the acids with more than 10 carbon atoms, they are wax like solid, not very crystalline solid, it is wax like solid, and their odor also diminishes. And the reason is now they are having higher molar mass, because now you are having more than 9 carbon atoms, so molar mass is increasing. As a result, volatility is also decreasing. Now when volatility is decreasing, there is a tendency to move towards vapor state, because when the molecules they are in gaseous state or vapor state, they are more they can come easily, that is we can smell them easily, right? Because they are more volatile, they are in highly energetic condition. So that is why we can have some their odor, but as now it is changing to wax like solid, so there will be decreasing volatility, and decreasing volatility means odor will also decrease. Odor diminishes. After physical state, solubility. Solubility of carboxylic acid. Carboxylic acid, they have the ability to form hydrogen bonds, and with low molecular weight, some measure of solubility in water. So even if it is very small size of, suppose, carboxylic acid with very low number of carbon, then also because of this hydrogen bond formation, because of this property, even if it is low molecular weight, then also they will have some solubility in water, because they can form hydrogen bond with solvent molecules. Which solvent molecules? Water molecules. So as they can form hydrogen bond, obviously there will, because of this interaction, they will be soluble in water. Carboxylic acid with 6 or more carbons now tend to only be slightly soluble. So when up to 5, solubility is fine. But now when you are reaching towards 6 or more than that, 7, 8, 9, now gradually the solubility will decrease. And that is very natural, because when you are going beyond 6 carbon, 7 carbon, 8 carbon, that means what? Now the hydrocarbon part, that is increasing. CO2H group is fixed, only one CO2H group. So keeping that part fixed, you are just increasing carbon and hydrogen. So hydrophobic part is increasing, so obviously solubility will decrease, even if there is hydrogen bond. But then also, as you are increasing the hydrophobic part, that is the hydrocarbon part, so obviously solubility will decrease. So see here in this picture, this is carboxylic acid, and we have 2 water molecules. So the oxygen end, that is, we have basically this C double bond O oxygen. This can interact with a hydrogen atom of water molecule. This is the negative end, this is the positive end. And also this H, as it is attached to electronegative atom oxygen, so this H also can take part in hydrogen bonding. And now this hydrogen of CO2H is interacting with the oxygen atom of water molecule. So both sides, they can form hydrogen bond, and because of this type of hydrogen bonding, there is some solubility in water, but it is max up to 5 carbon, not more than that. Here we have this table where you can see the formulas. HCOH, this is the first member possible, formic acid, the simplest carboxylic acid, and gradually we are increasing the carbon. So here carbon number is basically, except CO2H, there is no carbon. Then here gradually we are increasing the carbon number, right? In this case, that is number 4, we have 2 CH2, 1 CO2H carbon, 1 methyl. That means total 4 carbon, right? So if now we see the solubility in water, solubility gram per 1000 gram of water, you can see gradually when there is increase in number of carbon, there is also solubility is increasing. Fine. Now conversion to the corresponding carboxylate anion tends to immensely increase water solubility because of creation of an ion dipole intermolecular force. Now if we see, sorry, it will be one mistake is there. Here it is mentioned insoluble, it is not actually right, because it is 1 carbon, then 2 carbon, 3, 4. Fine. So here it is mentioned carboxylic acid with 6 or more carbons. That means here we have 5 and 6. So 6 and more carbon, as you can see, gradually it is diminishing, right? So all this will be not insoluble, it is soluble. Okay, just cross this in. So when it is formic acid, acetic acid, propanoic acid, butanoic acid, solubility is quite fine. But as we are further increasing the carbon number, solubility, so all these values that you are seeing, it is actually 5 gram in 100 gram of water. So maximum 5 gram of this molecule you can, that is solubility is possible in 100 gram of water. So as you can see, gradually the value is decreasing. And the last one is interesting. Here it is actually benzoic acid. Now in benzoic acid also the hydrocarbon part is large compared to CO2H, so that is why solubility is very low. Fine. Now the last point, that is, if you convert carboxylic acid to the corresponding anionic form, that means if you take some metal salt. So see, here we have this long carbon chain. So you cannot expect it to be soluble in water, right? So it is not water soluble. It has very long carbon chain, obviously more than 6, even more than 7. But when you are that is in presence of NaOH, now this H will be replaced by sodium. So now it is in sodium salt form. This is no longer carboxylic acid form, it is now sodium salt form. Any other metal, that is potassium, is also fine. So now what is happening, as it is now in anionic form, gradually solubility in water is increased. Now why it is so? Because of creation of ion dipole intermolecular force. So now you have fully developed negative charge over oxygen. But before treatment with NaOH, you simply have OH, where you do not have any negative charge. You have simply lone pair. And compared to lone pair, when you have fully developed negative charge, obviously the interaction with water will be better. So that is why when you are converting it to some metal salt form, because of creation of an ion dipole intermolecular force, now solubility is possible. So before treatment with NaOH, it is not soluble in water, but after treatment with NaOH, it is soluble in water. So the second physical property is solubility. Now based on this, let's see this problem. Which of the following aliphatic carboxylic acids is a solid at room temperature? Now to answer this question, you just have to check this first point, physical state. What it is mentioned? It is mentioned that when it is more than 10 carbon atoms, they are wax like solid. That means if it is less than 10, it will not be solid. If it is more than 10, then only it will be solid. If we look at the options, heptanoic acid, that means total 7 carbon atoms will be there. Then octanoic acid, total 8 carbon. Nonanoic acid, total 9 carbon. But when it is deca, now it is 10 carbon. That means you can expect this to be solid at room temperature. That is wax like solid. So this should be the correct option. Next question is related to solubility. Benzoic acid is almost insoluble in which of the following solvent? Now in the previous slide, what we have seen, remember in the last table, the last acid is benzoic acid, C6H5CO2H. If you consider water as solvent, it is 0.29 gram max you can, that is solubility is possible in 100 gram of water. Now the question is asking, benzoic acid is almost insoluble in which of the following solvent? So what are the solvents we have taken? Cold water, then we have taken benzene, ether and alcohol. Now benzene, ether, alcohol compared to water, obviously their organic character is more. Water is more polar in nature. Compared to water, these three, there will be less polarity. Now when less polarity, and in the table previous slide you have already seen that it is only 0.29 gram maximum solubility possible in 100 gram. And here it is even mentioned cold water. So obviously compared to BCD, even if it is normal water, then also it will be almost insoluble, because 0.29 gram in 100 gram, it is almost insoluble. 0.29 means 0.3 gram, right? And if it is cold water, then the insolubility that will even increase. That is solubility, it will be decrease further because it is cold. It is temperature is less than room temperature, right? So that is actually the correct answer. The large hydrophobic benzene ring of benzoic acid. So benzoic acid, C6H5CO2H. So except CO2H, if you consider this part, this is large hydrophobic C6H5. So because of this hydrophobic part, it prevents the carboxylic group from taking part in hydrogen bonding. Though hydrogen bonding is possible, but this factor will overcome the hydrogen bonding factor. These two are basically contradictory. So benzoic acid is soluble only in non-polar solvents, though I will not say that alcohol is very non-polar. Everything is relative. So when I am saying non-polar compared to water, obviously it is non-polar. But if you compare benzene and alcohol, obviously alcohol is more polar. But all these solvents, as these four solvents are mentioned, benzene, ether, alcohol, chloroform, all these, they can, that is in these solvents, solubility is possible. So see, cold water is the only option where solubility is not possible. So it is almost insoluble. Number 3, physical property is boiling point. Carboxylic acids are higher boiling liquid if you compare with aldehyde molecules, ketone molecules, esters, and alcohols. So if I write the general structure, it is RCHO, ketone is RCOR if it is symmetrical, ester is RCO2R, ester is RCO2, and alcohol is ROH. So compared to all these molecules, carboxylic acid, they are having higher boiling point. Though you have almost same value of molar mass, that is, molar mass is another factor based on which boiling point may vary. When molar mass is increasing, boiling point also increases. So as this factor is also responsible for boiling point variation, so you have to keep it fixed. So when you are keeping it fixed and you are comparing different types of molecules, aldehyde, ketones, ester, alcohol, carboxylic acid, now under this condition, when molar masses are almost same, under this condition, carboxylic acid will have highest boiling point, and the reason is it can form intermolecular hydrogen bonding. In the previous slide, you have seen in the solubility point that hydrogen bonding with water molecules, where water is basically solvent, that is possible. And that is hydrogen bond formation between carboxylic acid molecule and water molecule. But now the intermolecular hydrogen bonding that I am saying, what it means, that between two carboxylic acid molecule, hydrogen bond formation possible. Here we are not considering hydrogen bond with solvent because we are considering boiling point. And boiling point means what? That is conversion from liquid state to vapor state. Now when boiling point is high, that means this conversion is very difficult. And when boiling point is low, that means this conversion is very, you can do it very easily. So when it is difficult, that means there must be some strong interaction, and this interaction is basically intermolecular hydrogen bonding. And because of this intermolecular hydrogen bonding, they remain in the form of dimer. So see, this is one carboxylic acid molecule. This is another carboxylic acid molecule. And what type of interaction is going on? This carbonyl group oxygen, it is interacting with the H of another hydrogen atom of another carboxylic acid molecule, and vice versa. This H is interacting with carbonyl oxygen of another carboxylic acid. So because of this type of dimer formation, not only in the liquid state but even to some extent in the gaseous state also, this dimer exists. Fine. Now when it is always present in liquid state, because in liquid state the molecules can come close to each other, so hydrogen bond formation will be facile process compared to gaseous state. But here we are talking about boiling point. So if in liquid state they are very close to each other, they can form dimer. So when you are converting it from liquid state to vapor state, so obviously now you have to break all these hydrogen bonds, which is really difficult process because this is very strong. So that is the reason compared to other molecules, ketone, aldehyde, they will have higher boiling point. And most carboxylic acid exists as dimer in the vapor phase, and also it is possible in the aprotic solvent. Aprotic solvent means where active hydrogen is not present. Now water is protic solvent, and here the hydrogen, as it is directly attached to oxygen, I am talking about water molecule. So they are protic solvent, and in protic solvent, hydrogen bond formation is possible with the solvent molecule. But if the solvent that you have taken, it is aprotic type of nature, now bond formation, hydrogen bond formation with Aprotic solvents not possible. For example, acetone, CH3, CO, CH3. Here you do all these 6 hydrogens, they are not attached to any electronegative atom like oxygen. They are attached to carbon. So these hydrogens are not active. So this is aprotic solvent. And if you take carboxylic acid in aprotic solvent, hydrogen bond formation between a carboxylic acid molecule and one solvent molecule, that is not possible. So they can now hydrogen bond with themselves between two same carboxylic acid molecules. So that is, it is mentioned in the last point that most carboxylic acid exists as dimer in vapor phase, and also if the solvent you have taken in which you have this carboxylic acid, if it is aprotic type of nature, then also dimer formation is possible. And in liquid state, it is always in dimeric form because now they are close to each other. So chance of hydrogen bonding will increase. So look at this table. Here in the left hand side, we have different types of molecules. The first molecule is carboxylic acid, then we have alcohol, the third one is aldehyde, fourth one is ester, C, RCO2, R prime. The fifth one is also ester, and the last one is basically hydrocarbon. Now, why we have taken specifically these molecules? You can also check the names. This is carboxylic acid, alcohol, this is aldehyde, these two are ester, and this is simply alkane. Now we have taken this because if you look at the third column, their molecular weights are almost same, varying 86 to 88. So when molecular weight is fixed, almost fixed, I mean, now you can compare what is the effect of this group, CO2H group, OH, CHO, then RCO2, R prime, and there is no group, the last one. Now see, the lowest one, that is boiling point, this is lowest, 69, and it has to be because it is hydrocarbon. There is no electronegative atom, only interaction present is with van der Waals interaction. So you can easily convert them from liquid state to vapor state. But as you are moving towards ester, now see gradually the values are increasing. In aldehyde also it is 103. Difference between alcohol and aldehyde is also high, 103, 138. Because in alcohol also some amount of hydrogen bond possible, but not to that extent that you can expect in carboxylic acid. Here maximum hydrogen, that is hydrogen bond formation, that strength is very high. So that is why maximum boiling point. Fine. And here if you are interested, water solubility, that is also mentioned. It is insoluble because it is hydrocarbon. Then these two are gradually solubility is increased. Here also slightly soluble, both aldehyde and alcohol. And this is also very soluble because they can not just form hydrogen bond between two individual carboxylic acid, but they can also form hydrogen bond with water molecules. So that is why their solubility is also very high, not just boiling. So here we have the third point, third physical property, which is boiling point. Compared to any other groups, when molecular weight almost same, then you can compare the boiling point. It is having the maximum boiling point. Which of the following is not a reason for carboxylic acid having higher boiling point? Now, why carboxylic acid are having higher boiling point? There may be compared to alcohols of comparable molecular masses. This must be mentioned clearly because if it is not fixed, then you cannot compare these two different groups because molecular weight is another factor based on which boiling point may be different. So when it is same and carboxylic acid, they are having higher boiling point compared to alcohols, what is the actual reason? That if you know, then only you can understand which is not an actual reason. Fine. Now look at the options. We have to find that statement which cannot be a reason for its high solubility. The first option is saying that presence of electron withdrawing carbonyl group. Now alcohol is ROH, and when I'm saying carboxylic acid, it is RCOOH. That means now this part is fixed, but you have extra C double bond O, which is electron withdrawing group. So obviously now the hydrogen bond that will be formed between two RCO2H. That will be very strong compared to the hydrogen bond that is possible between two alcohol molecules. So this is obviously a reason for its high boiling point, because of this group. Now hydrogen bond strength is high, and when hydrogen bond strength is high, boiling point will also be high. So this is obviously a reason, and this cannot be our correct option. Second statement is higher polarity of OH bond than in alcohols. Now this part is fixed OH-OH, but if you consider polarity of the OH group of carboxylic acid and the OH group of alcohol, obviously in this case, because of presence of this electron withdrawing group, now the polarity of this OH bond, that will be high compared to the OH bond that is present in alcohol. So this is also a perfect reason why it is having higher boiling point compared to alcohols. The third point, formation of two hydrogen bond to form cyclic dimers. Now we have already seen cyclic dimer formation, as you can see in this slide, intermolecular hydrogen bonding between two carboxylic acid. So from both sides there is hydrogen bond formation going on. You are getting that is cyclic type of structure, right? So which is very stable, ring type of structure. So this is also a reason why they are having higher boiling point. So A, B, C all are basically the correct reason. But the last point is saying that presence of more alkyl group in carboxylic acid. Now this cannot be the correct reason. That first of all, here when we are considering general structure having almost same molecular mass, right? Now same molecular mass, just have a look in the previous slide. Suppose you have this alcohol, 1-pentanol and butanoic acid. Fine. When both are having same molecular weight, this is CH3 CH2 whole 4. That means total 5 carbon. And here we have CH3, then CH2 2 times. That means 2 carbon and 3 carbon. So when molecular weight are same, then if you look at the hydrocarbon part, then in alcohol it is actually high, and that has to be because when molecular weight is fixed, you have one C double bond O extra compared to OH. So obviously now in the hydrocarbon part of alcohol, that will be large compared to hydrocarbon part of carboxylic acid when molecular weight is fixed. So first of all, the statement itself is wrong, that presence of more alkyl group in carboxylic acid. No, when molecular weight are comparable, presence of more alkyl group, that is in alcohol, not in carboxylic acid. And even if there is more alkyl group in carboxylic, this is not the actual reason for higher boiling point. Fine. It will be true only if you have taken one carboxylic acid to one alcohol not having comparable molecular masses. Suppose carboxylic acid is having very high molecular mass compared to alcohol, then you can say that more alkyl group is present. But when comparable mass, we cannot say this is the correct reason. So option D will be the correct one, because it is not a reason for carboxylic acid that it can have higher boiling point than alcohol. If the boiling point of propanol means CH3, 3 carbon, then OH. So this is propanol. Its boiling point given 370 Kelvin in Kelvin scale. Predict the boiling point of acetic acid. Now acetic acid means 2 carbon. Right? Now here the values that are given in option 322, 329, 370 and 390. Now 370, and if you look at the values, only these three values, this is same 370. A and B, they are lesser than 370. C, option C is same value, and option D is higher value. Right? Now we know that when comparable molecular mass is present, then compared to alcohol, now carboxylic acid, they will have higher boiling point. So if we check their molecular masses, they are actually having same molecular mass. Now why it is so? If you just write the total number of carbon and hydrogen and oxygen, It will help you to understand. So it is C2O2H4, and here it is actually even if total number of carbon hydrogen not same, if you consider the final molar mass, it will be same. Here it is C3, then total number of hydrogen 8, total number of oxygen O. Fine. Now C3H8O, you consider 3 into 12, 36 plus 8 plus 16. Fine. So it is 0, 60. And if you consider it here, it is 12 from carbon, sorry, 24 from carbon, 16 into 2, 32, and 4 from hydrogen. Now if I write it 28, see, this is actually same. So in this way you can understand, as they are having same molecular mass, even if it is not exactly same, if it is very close to each other, then also it is same. You can apply the same logic. Acetic acid will have more boiling point because propanol is alcohol. So in alcohol, hydrogen bonding is possible, but not, its strength is not like the hydrogen bond that you can find in acetic acid, that is carboxylic acid. So that is why these three options cannot be correct, because 370 is same, these two are less, only the last one is high, 390 greater than 370. So that is, this is the correct option. Predict the boiling point of acetic acid, only this value is higher than 370, so that is, it is the correct option. Now after finishing physical properties, next we will see acidic property. Now you cannot say exactly it is physical property, because based on this acidic property, it has direct impact on the chemical behavior. So that is why it is discussed not under physical property, it is discussed separately. As we say carboxylic acid, so from the name you can understand they must have some acidic property. Otherwise, why we are calling it carboxylic acid? We don't call aldehyde or ketones by the word acid, but carboxylic acid by the word acid. So there must be some reason. So the most important property of carboxylic acid, and the one that is responsible for naming them such, is their acidity. Clear from the name itself. So suppose the general structure, if I write for any acid, not just carboxylic acid, HA. So in carboxylic acid, you can consider this part is the RCO2 part. Okay. So when it is in presence of water, it is forming hydronium ion, and this is the conjugate base. Because this bond is broken, A is the conjugate base. I am writing Cb. K equilibrium for this reaction. Whatever species you have in the right hand side, just take the concentration and divided by the undissociated HA, because all the molecules will not be ionized. So this is the undissociated HA. Water is also present as solvent. Sometimes it is ignored because it is present in large excess, right? So you can also write, when it is K equilibrium, we write it in this way. But if you consider the dissociation constant, which is Ka, now you just write only H3O plus concentration, A minus concentration divided by undissociated HA. Fine. Now if we take both side log, then what we will get? Suppose if you are taking log Ka, and also if you put a negative sign before it, now this will be equal to pKa. Okay. Now you can also write it in this way, log 1 by Ka, because there is a negative sign. So this is the definition of pKa, negative logarithm of Ka. So you also have to take negative log of all these concentration terms. Fine. So carboxylic acid, they can donate H plus readily than most other classes of organic compounds. You can also consider ROH, that is alcohol. But here you are getting RO minus and H plus. But this dissociation, if you compare with the dissociation of carboxylic acid, obviously this is not so significant. Fine. Because in this case, the conjugate base that you are getting is alkoxide ion, RO minus. Suppose if it is methanol, it is MEO minus. If it is ethanol, it is ETO minus. Now these conjugate bases, they are not very stable. But if you consider the conjugate base of carboxylic acid, now its stability is more, because now the conjugate base, it is having this type of nature, and this conjugate base, it is very stable because this type of resonance is possible. So after resonance you are getting similar structure, and in resonance when we get similar type of structure, that is very stable. So as their conjugate base is very stable compared to conjugate base of alcohol, so obviously the equilibrium will be shifted towards right hand side. So these two species, their concentration will be high, and as this is very high, that means log of these values, that will be very high. But as there is a negative sign, that means when pKa is very less, that means acidity is very high. Or you can say that when Ka is very high, then acidity is directly related, acidity is also very high. But as pKa means negative logarithm of K, now when pKa is high, that means acidity will be less, inverse relationship. So there, compared to other organic classes of organic compounds, they are very strong acid, but don't think that they are stronger than this inorganic acid. We call them mineral acid, H2SO4, HNO3Cl. So these three are very important in organic acid. So in organic compounds, carboxylic acid, they are the maximum, having maximum acidity, but don't think it is even stronger than mineral acid. No, they are much weaker than the most important mineral acids that we mostly deal in inorganic chemistry. But in organic chemistry, carboxylic acid, their acidity is maximum, and the reason is here conjugate base is very stable because of this type of resonance. And when conjugate base is very stable, obviously this dissociation from undissociated form to dissociated form, that dissociation will increase. And when dissociation increase, that means now the concentration of H3O plus is very high, and concentration of H plus high means what? Acidity is also very high. Okay, so that is why they are most acidic if you consider only in organic, that is the classes of organic compounds, not don't compare with mineral acids. Fine. Now as this is the logic behind this acidic property, now we will compare some values. So here pK value is mentioned for ethanol, phenol, ethanoic acid. So this is alcohol, this is also alcohol. Look at the pK value as it is mentioned. When pKa is very high, that is inverse relationship, that means acidity will be low. Now look at the value, this is very high, this is 10, that means phenol to some extent more acidic than ethanol, because here the conjugate base after dissociation that you get, it is phenoxide ion, which has some resonance stability. The negative charge can take part in resonance with the CC double bond. So that is why compared to ethanol, phenol will have high acidity. But now look at the value of ethanoic acid, 2 carbon carboxylic acid, 4.76. So this is much acidic compared to phenol and ethanol. Okay. Here we have some benzoic acid derivative. So the first one you can see, chloro substituted benzoic acid. Chloro in ortho position, meta position, para position. Now look at the pKa values. It is maximum acidic when it is ortho, after that meta, and then it is para. So the reason for this type of behavior is that chlorine, it has minus I effect, and minus I effect, it decreases with distance. So when it is at 4 position, its minus I effect is not so strong when it is at 2 position. So that is why ortho is maximum acidic, then meta, then para. And when you are considering it, don't consider the plus R effect of Cl. Here minus I effect of halogens is mostly considered. So this is the order. Now for NO2, that is a second example. Now the order is maximum again ortho, just like the previous. But after ortho it is not meta. After ortho it is para. And the reason is NO2 has both minus I effect as well as minus R effect. Now if you consider minus I effect, it should have the same order as you have seen in case of chloro. But here minus R effect is also present, and minus R effect is more important compared to minus I. So ultimately If these two are contradictory to each other, minus R effect will win, and minus R effect is possible only at ortho position and para position, not meta position. So that is why when it is at ortho, both minus I effect maximum as well as minus R effect, and that is the ortho is maximum. After that, among meta and para, in meta only minus I effect, but in para both minus I as well as minus R. So that is why after ortho it is para, which is clear from the pK value, and then it is meta. Fine. And the last one is, now we have NH2 group. Now NH2 group we have to consider plus R effect, and plus R effect means donating effect, so it will decrease the acidity. Fine. So maximum acidic it will be now meta. Why it is so? Because plus R effect is not possible from meta, and plus R effect it is basically decreasing acidity, and it is possible only at ortho and para position, not meta. So meta will have maximum acidity, and after that it is para and ortho, because when it is at para position, now compared to ortho position, plus R effect will be less. So that is why after meta, para will be having maximum acidity, and then it is ortho. So here we have different benzoic acid derivative. The first example chloro, then NO2, which is electron withdrawing group, and the last one electron donating group, which is NH2. Not just these three groups, if you look at this table, you can find, see, this is the position of X. It is written in this way. That means X may be at 2 position, X may be at 3 position, X may be at 4 position, or it may be at both ortho position, that is 2 and 6. So when OH group it is present at ortho, meta and para, how the acidity is changing, just apply the logic of minus I effect or plus I effect, or plus R or minus I effect. Applying all these effects, you can understand why this type of variation is there. Okay, so different halogens are there. Then we have alkyl groups. After FCl BRI, we have alkyl groups. Okay, then we have some donating group. NH2 we have already seen. OMe, that is another donating group. NO2 also we have seen. Then simply H, that means no substituents are there. So that is why I see only one value is there, because no substituents means no question of ortho meta para. Then we have also CO2H group. That is, if it is dicarboxylic acid, then also you can check how their acidic behavior that will be changing with the position of second CO2H group. Okay, so this table will give you this order of different, that is order of acidity of different substituted benzoic acid. Fine. Now we have some aliphatic, not just carboxylic acid, some alcohol molecule also. If you look at the first example, this one, here we have water, then we have hydrogen peroxide, so we have water, then we have H2O2, hydrogen peroxide. So pK values are given so that you can compare how the changing with OH group and C double bond O, that is carbonyl group, which is present in carboxylic acid only, how the pK values is changing. When it is water, it is 14. Then as one H oxygen is increased, now acidity is slightly increased. Then we have this molecule which is basically 2H group attached to same carbon. Now as we have 3 chlorine, so compared to hydrogen peroxide, now it will have more acidity. Then we have CF3CH2OH. Now as CF3 group is not directly attached to OH, so that is why acidity is not so high. Now we have some carboxylic acid derivative, formic acid, acetic acid. Now the next one, this is also acetic acid, only difference one H is now replaced by F. And see, just change one H with F, how drastically the pK values is changing. So F is very electron withdrawing group because of minus I effect. Now it will draw electron density towards itself. You can also see the direction of arrows. As a result, the polarity of this OH bond will highly increase, and this bond you can easily break. H plus you can easily get, that means acidity is very high. And when you are also replacing the other two hydrogen with 2 fluorine. Now you have total 3 fluorine. Now look at the value, it is 0. That means very, very acidic in nature. Now the third row, here we have CO2H group, but it is not directly attached to chlorine. In between chlorine and CO2H, we have total 3 CH2. Now this is 4.53. In the next example, now the chlorine is closer to CO2H. So more close it is, gradually acidity is increasing. And in the last example, Cl is even closer. So now it is 2.8. So in this way, you can understand that the effect of electron withdrawing group, how it is changing the acidity of carboxylic acid. Fine. So the first row, it is basically not carboxylic acid, there are some OH group, but the second row, this is carboxylic acid. Only we are changing this. First we have changed this H with CH3. Here also you can find some difference. From 3.75 now it is 4.74. Why? Because if you compare H and CH3, CH3 it has some plus I effect. So because of this donating effect, it will decrease the polarity of this OH bond. But that is not possible in case of formic acid, where you have only H attached to CO2H. So that is why pK of formic acid compared to acetic acid is less. And less means acidity is high because it is reverse relationship. But in acetic acid, when you just change one H with F, now it is drastically changed. Even it is more acidic than formic acid. And when all this, that is all the 3 hydrogens are replaced by F, now it is 0. So acidity is very, very high. So the more you practice the order of acidity of carboxylic acid, both in aromatic, non-aromatic, you will have more idea, because questions related to order of carboxylic acid, it may be aromatic or non-aromatic, that is very, very common. So if you know the proper logic, you can easily identify what is the correct order of carboxylic acid. Today we are at the end of the session. We'll end the class here. Thank you for listening.